Let's look at another type of two-body problem. This one is called the Atwood machine, and it consists of a pulley and two masses. We'll call this M2, and we'll call this M1. And we'll say for this problem that M2 is greater than M1. There's no friction in the pulley is massless or a very negligible mass, and the string has negligible mass as well, which of course implies that if M2 is greater than M1, that this is going to go down this way and this is going to go up. That's going to play a role in our calculations. And again, we're going to do this one theoretically just using the symbols themselves without numbers. You do learn a little more physics doing it this way. So let's start off. And again, there are two steps. One, you draw the free body diagrams, and then two, write Newton's second law for each diagram, and X and Y for each mass. So the free body diagram, step one, for each one would be, we'll have M1 here, M1, and M2 here. And now we're going to write the forces that occur for each one of these masses. If we look at M1, we can see, what do you think? There's a string pulling up on it, right? There's a cable pulling up. That's going to be an upward tension. And then it's going to have a second force, which is the weight going down. And we'll call that M1 times G, weight. Mass 2 is really in the same situation. The string is holding it up, so that's going to be tension, which of course, since it's the same string, it is the same tension. There's no friction in the pulley. The pulley is, as I said, negligible mass, so that tension will be the same. That's a key factor. You can solve problems where there's friction in the pulley, but then you have to know a little bit more about circular motion in order to do that, and inertia of rotational objects. But for now, we don't have to worry about that, and we have M2G going down. All right, so that's as simple as it gets there. There is now, however, something we have to take into account. This one, as we said, is going to be going up. That means that up is positive. That means this will be positive, this will be negative. M2 is traveling downwards. Therefore, downwards is going to be positive, and upwards will be negative. We're consistent here because as long as the object is moving in this direction here, we have to be consistent in that way. If we put them both positive upward, the objects would no longer actually be connected to each other. They'd both be going up at the same time. All right, so now we're going to write Newton's laws down. And we don't have any X forces, so that simplifies it a lot. We only have forces in the Y direction. So we're going to write the sum of the forces in the Y equals M1A, and the sum of the forces in the Y equals M2A. And that's it. There are two forces in the Y direction and two forces in this Y direction. Where the difference arises is when they're plus or minus. So we've got M1A. And on the left side, what are our forces? How do they sum? Well, we've got tension going up and M1G going down. So T minus M1G equals M1A. And that's pretty much it. In the next mass, mass 2, we have minus tension plus M2G, and that equals M2A. Well, of course, for each equation, we're interested in, what we're ultimately interested in doing is find the acceleration for these things, and perhaps the tension too, but the tension is always easier to do once you know the acceleration. To solve for the tension first is actually a little, I don't want to say more difficult, but it has more steps to it. It's easiest to find the acceleration first. So that's what we want to do. If you can do that, then any of the other problems associated with these are fairly straightforward. They use kinematic. How far did it fall? How fast is it going after 1 second? That's all kinematic questions. But these are, the trick is to find the acceleration for these. So there's a number of ways you can do this. And the way, one way we can do it is this. We can solve for the tension in this one. And we say the tension equals M1A plus M1G. That's one way. And then we can plug this into here. So we get minus M1A plus M1G. It's important to put the parentheses around there to remember that you have to distribute the minus sign. Don't rush, okay? Don't rush to do these because that's when you make mistakes. So we have minus M1A minus M1G, we distribute the minus sign, plus M2G equals M2A. And now we want to collect the A's to one side of the equation because we want to solve for acceleration. So we have to collect like terms. I'm going to add M1A to both sides so that we end up with M minus M1G plus M2G equals M1A plus M2A. And now we see a pattern very similar to what we saw in the first graph. And let's see if I can straighten this out here. Okay, so what we want to do is we see a familiarity. We see M1A plus M2A. So we want to factor out the acceleration from that. So we get M1 plus M2 times A. And then we're going to divide both sides by M1 plus M2. And if we do that, we get minus M1G plus M2G over M1 plus M2. And we'll switch around the minus signs there. We get A equals M2G minus M1G over M1 plus M2. And what we can see is that if you compare this to the previous example we did, where we just had M2G over M1G in the previous example, where we had this situation, M2, M1, we found A equal M2G over M1 plus M2. You can see what's happened here. We've now included an extra term in the numerator. M1G, we're reducing the acceleration because that's kind of a counterweight, acting as a counterweight to the dropping mass M2G, where it hadn't been in that first thing. So note the difference here, and this is where we see a little bit of physics coming in. We see that now we've modified that original equation by having M1 drop as well. If M1 were greater, then the signs would shift around. You'd have a plus M1 minus M2G. Okay, so this is our equation for an Atwood machine. Atwood machines are typically kind of like counterweights. You might find them in elevators and things like that. All right, that's it for this video.